Today, we're peering deep into what we've called the hidden engine of modern science. We're diving into uh, array programming.
Which might sound super technical.
It does, but it's the absolute bedrock of numerical computation, really, across the globe. It's all about using this powerful, compact syntax for handling data, in vectors, matrices, and even higher dimensional arrays.
Tensors, right.
Exactly. And our focus today is on the library that made this whole approach foundational in Python, NumPy. So our mission for you listening is to really understand how this core open source library underpins, well, pretty much all modern scientific computing in Python.
And how it's adapting, because it's under some intense pressure right now from big data and all this specialized hardware we're seeing.
That's a huge piece of it.
It's truly impossible to overstate NumPy's role. I mean, if you think of Python as the lingua franca of data science,
Which it is.
then NumPy is the underlying grammar. It's that solid, non-negotiable foundation that the entire scientific Python ecosystem is built on. I'm talking machine learning, astrophysics, everything.
And it's not just academic. The source material had some pretty incredible examples.
Oh, absolutely. When we talk about these landmark, high-profile discoveries in the last decade, NumPy was right there, in the engine room. For instance, it was a key part of the software stack used in the initial processing that led to the discovery of gravitational waves.
At LIGO, right?
At LIGO, exactly. And maybe even more visibly, the analysis that generated that first iconic image of a black hole.
The Event Horizon Telescope.
That collaboration relied heavily, on the principles of array programming, all executed through NumPy. This is how world-changing science actually gets done.
Okay, let's unpack this then. Because something this critical, it never just appears out of nowhere. Before NumPy unified everything, the source material tells us there was fragmentation.
That's the perfect word for it, a real problem. Before NumPy arrived in 2005, the field was basically split in two, and that division was really hampering growth.
So what were the two camps?
You had two main contenders. First, there was the numeric package. This was developed way back in the mid-90s, a true pioneer. It was written largely in C, which is key for speed, and it focused on really strong performance for small arrays.
And it found a home in places like, what, high-performance computing?
Exactly. Things like inertial confinement fusion research. But then its rival appeared, and it was designed to solve a totally different kind of problem.
The scale problem.
Precisely. You have these massive astronomical data sets coming in from telescopes like Hubble, and a team realized numeric just wasn't built to handle data that was larger than a computer's physical memory.
So they created a re-implementation.
They did. They called it NumArray. And it was this necessary evolution because NumArray added really important features like better indexing and, crucially, memory mapping.
Memory mapping. For you listening, that's basically a way to treat a huge file on your hard drive as if it's already in your computer's RAM. It's how you deal with data that's just too big to fit.
Exactly right. But here was the core problem. Numeric and NumArray. They were similar, but just different enough in their APIs that it divided the community.
That sounds like a serious roadblock. I mean, if half your community is using one tool and half is using the other, how do you build anything on top of that?
You can't. That's the critical insight. The fragmentation was stifling the creation of all the higher-level libraries we know today. So the solution came in 2005 with NumPy. It was a conscious effort to create the best of both worlds.
So it took NumArray's features for large data.
Right, like memory mapping, and merged them with the speed and, this is key, the rich C API from Numeric.
Okay, hold on. When you say rich C API, what does that actually mean for a Python user? Is it just about speed?
It's so much more profound than just speed. It's about interoperability. It means that NumPy exposes its underlying data, that block of memory, through a standard C interface.
So other languages can talk to it directly.
Exactly. Highly optimized code in C or Fortran can read and write the data directly without any copying. That's the bridge. Without that API, you'd be constantly copying data back and forth between Python and these other libraries, which is just excruciatingly slow. This unification solved the schism and really allowed the whole ecosystem to just explode.
That merger paved the way for everything. Okay, so let's get into the anatomy of it. The basic building block, the NumPy array. It's not just a fancy list of numbers.
Not at all. It's a specific data structure designed for efficiency. A NumPy array is a fast, contiguous block of memory. A standard Python list, on the other hand, just stores pointers to data that could be scattered all over your RAM.
Okay, so we have a pointer to this continuous block of memory. What else does NumPy need to know to actually interpret that raw binary data?
Right, that's where the crucial metadata comes in. There are three main pieces. First is the data type.
Meaning everything in the array has to be the same type.
Exactly. All 32-bit integers or all 64-bit real numbers, every single element takes up the exact same number of bytes. That uniformity is a huge part of what makes it so fast.
Okay, so data type, what's number 2?
The shape. This is just the number of elements along each axis. It defines the dimensionality. A one-dimensional vector is easy to picture, but you can have a four-dimensional array, like a color video, which might have a shape of, say, time, height, width, and color channels.
And the third one. This is the one that the sources call the aha moment.
Yes. Strides. This is the secret sauce. It's the key to how NumPy interprets that linear block of memory as a multidimensional array. A stride just tells NumPy how many bytes to jump forward in memory to get from one element to the next, or from one row to the next.
Let's slow down on strides because this feels like the technical nugget that makes it all work. You said the data is contiguous in memory. Why is that so revolutionary for speed?
It all comes down to the CPU's cache. When your CPU needs data from memory, it doesn't just grab one byte. It grabs a whole block of surrounding data and puts it in its super fast cache memory.
Assuming you'll need the next piece of data soon.
Exactly. If your data is scattered all over, like in a Python list, the CPU has to keep going back to slow main memory. But with a NumPy array, the data is contiguous, so the next element it needs is probably already sitting right there in the fast cache. It's a massive automatic performance boost.
Which makes that strides example even more important. So give us that crystal clear scenario from the sources.
Okay, imagine a simple two-dimensional array. Let's say it has a shape of four rows and 3 columns, and each element is an 8-byte number.
Got it.
To move from one column to the next, inside the same row, you just have to jump forward 8 bytes. Simple enough.
Right.
But to jump from, say, the first element of row 1 to the first element of row 2, you have to skip over all 3 elements in that first row.
So 3 elements times 8 bytes each, 24 bytes.
Precisely. So the stride for the columns is 8, and the stride for the rows is 24. The strides for that whole array are just a pair of numbers, 24, 8. NumPy just uses that simple math for lightning-fast indexing.
That is elegant.
Mm-hmm.
So knowing that efficient memory handling is happening under the hood, what does this actually look like when you're writing code?
The goal is to give you this readable, expressive, high-level API, but keep all that C-level speed. And that's achieved through 2 main concepts.
Okay.
First, and this is the heart of the whole paradigm, is vectorization. It means you operate on entire arrays at once, not element by element in a loop.
I remember when I first started programming, if I wanted to, say, take the square root of a million numbers, I had to write a manual for loop. It was slow and the code was messy.
Exactly. Vectorization gets rid of all that mess. In NumPy, taking the square root of an array with 1,000,000 elements is just one clean expression. np.sqrt, my array. You just focus on the science, and NumPy handles the low-level looping optimally, taking full advantage of that CPU cache.
And the second concept, broadcasting, that solves the problem of shape mismatch, right? If I'm adding a single number to a giant array, how does it not just throw an error? It's not secretly copying data, is it?
That's the critical question, and thankfully, no. Broadcasting is this incredibly smart mechanism that lets you do operations even when dimensions differ, and it avoids all that unnecessary memory copying.
So your example, adding the number 5 to a giant 1,000 by 1,000 array.
Right. Instead of making a whole new 1,000 by 1,000 array filled with 5s, NumPy just virtually duplicates the number 5 so that the shapes match logically. It's a huge memory and speed saver. It's pure genius in its simplicity.
And it's not just the basic math operators. NumPy bundles in a whole suite of optimized functions.
It does. You get vectorized functions for statistics, like sum or mean, and critically for linear algebra. And these aren't just written in Python.
Right, they use backends. The sources mention things like OpenBLAS and Intel MKL. What are those?
They're highly optimized libraries, usually written in C or Fortran, specifically for speed. OpenBLAS is an open source one, and Intel MKL is Intel's proprietary version. These are routines written by absolute experts to squeeze every last drop of performance out of a modern CPU. NumPy just acts as the Python wrapper that calls on these super fast libraries.
So you get hardware-optimized math instantly without ever leaving Python.
That's the synergy. Python is easy to learn, and adding this speed means scientists can do almost all their work in one language. No more context switching.
And that integration is what created the ecosystem.
Exactly. NumPy didn't exist in a vacuum. It enabled a software revolution. The core of that foundation is NumPy, plus SciPy, which provides more advanced algorithms.
And matplotlib for visualization.
Right, and then you combine those with interactive tools like Jupyter Notebooks, and you have the scientific base.
And it basically became the standard format for exchanging data between all the other big libraries.
It's the universal lingua franca. Pandas for data analysis, scikit-learn for machine learning, scikit-image. They all store, manipulate, and pass around NumPy arrays. If you want your library to be fast, it has to speak NumPy.
Let's go back to that black hole image, because that really makes this concrete.
It's the perfect example. The 8 imaging library, which processed all that data from the telescope, it lives on this stack. NumPy arrays stored the numerical data at every single stage. SciPy provided filters and Fourier transforms. Scikit-image added higher-level tools. And Matplotlib, of course, made that final iconic image.
You also mentioned that this is about culture, too.
Yes. The NumPy community adopted professional software engineering practices very early on. Things like version control, continuous testing, high-quality documentation. And that culture spread. It's vital because contributing to these projects gives junior scientists real-world software development skills they often don't get in a formal university education.
So this stability made it the bedrock. But then, 15 years later, the sheer scale of modern data created new problems. How did NumPy face that without fracturing the community all over again?
The challenge was immense. First, datasets just got too big for one machine's memory. Second, deep learning brought on this wave of specialized hardware.
GPUs, TPUs.
Exactly. And NumPy was designed for in-memory arrays on a CPU. It couldn't use any of that new tech.
So you risked another numeric versus numeric schism, CPU arrays versus GPU arrays.
And the community learned its lesson. New array packages did emerge: PyTorch, TensorFlow, Dask for distributed data, CuPy for GPU data. But crucially, they all decided to mimic the NumPy API.
So if you know how to use np.mean and NumPy, you already know how to use the Dask or CuPy version.
That's it. They adopted the same high-level interface. It dramatically lowered the barrier to entry. You didn't have to learn a whole new programming style just to use a GPU.
It sounds like NumPy's role was shifting. It went from being the main workhorse to something more like a central coordinating mechanism.
Precisely. NumPy now provides these formalized protocols or contracts that define how an array object should behave. This allows these specialized external arrays, like one from Dask or one from CuPy, to be passed directly into a standard NumPy function like np.mean.
And what happens then? Does NumPy just hand off the job?
It acts as a smart dispatcher. It sees the object, checks that it follows the protocol, and then directs the operation to the right underlying library. The payoff for you, the user, is phenomenal. You write your code once with the familiar NumPy API, and then you can scale it to a massive multi-GPU system just by changing the type of array you create at the start.
Wow.
You can even embed CuPy arrays inside Dask arrays, and suddenly you're running your code across millions of cores on multiple machines with almost no changes to your script. NumPy becomes the universal standard API for tensor computation.
That brings us to the end of our dive. So if we zoom out, NumPy's identity is really clear. It successfully combined the expressive power of array programming, the raw performance of C, and the readability of Python into this core scientific infrastructure.
And its role keeps expanding. It's still the foundational library, but now it's also the standard API and the central coordinator between all these different systems and hardware.
And it's poised to face huge challenges. More users, data from things like the Large Synoptic Survey Telescope, adapting to ideas from new languages like Rust and Julia. But for this open source infrastructure to meet those needs, it needs sustained funding.
It does. And that leads us to our final provocative thought for you. The future viability of this bedrock technology doesn't just depend on its technical adaptability or on funding. Fundamentally, it depends on its ability to attract and nurture a new generation of graduate students and community contributors to actively drive it forward. In the end, the most important source of computing power might just be the open source community that decides to volunteer their time to keep this engine running.